Okay, so this is about alkenes, which is also a family of hydrocarbons. The alkenes. The other family, the other homologous series. Now, the homologous series of alkene is CnH2n. That's the general formula of all alkenes. N represents the number of carbon atoms. So if, for instance, you have ethene with 2 carbon atoms and 2, there will be 4 hydrogen atoms. So the formula of ethene will be C2H4. Propene with 3 carbon atoms, we have 6 hydrogen atoms. So the formula of propene is C3H6. Also butene or but1ene with 4 carbon atoms, we have 8 hydrogen atoms. So it will be C4H8 for but1ene. Now, alkenes are also hydrocarbons because they contain only hydrogen and carbon. Hydrocarbons contain only hydrogen and carbon. They are part of the organic compounds. Organic compounds, some other organic compounds may contain other elements like hydrogen. For instance, alcohols may contain oxygen too. Carboxylic acids, which are also organic compounds, may contain other compounds like oxygen. But hydrocarbons have only hydrogen and carbon as the 2 elements. The organic compounds that are hydrocarbons are alkanes and alkenes. We've talked about alkanes before, so this is about alkenes. So alkenes are hydrocarbons. They form a homologous series CnH2n, and they all contain carbon-carbon double bond, which is their functional group. Compare it with the previous one we talked about, which is alkanes. Alkanes contain a carbon-carbon single bond. And because alkenes have carbon-carbon double bonds, they are unsaturated. Unsaturated means they can be broken down further. Unlike alkanes, which have a single bond which cannot be broken down further into any other one. And because they are unsaturated, they can form other substances, usually some other useful substances. In fact, they are more reactive. Unsaturated hydrocarbons are more reactive than saturated hydrocarbons. Unsaturated hydrocarbons are more reactive because they can form other substances like plastics, pens, shampoos, and what have you. Okay. So that's how the covalent bond looks for ethene, for instance. It is unsaturated because it has a carbon-carbon double bond, which can be broken down into a carbon-carbon single bond, alkanes that are now saturated. So alkanes have only single carbon-carbon bonds, so are saturated, while alkenes have carbon-carbon double bonds, so are unsaturated and so more reactive. Now, for instance, these are the structural formula of the first 3 alkenes: ethene, propene, and butene. Remember, ethene has 2 atoms of carbon. Propene has 3. Butene has 4. There cannot be a methene. Methene has 1. There must be 2 bonds with the carbon. That's why you cannot have a methene. There can never be any methene. There won't be any methene. No way. The reason is you need to have at least 2 carbons with a double bond. There's always a double bond in all alkenes. That's why there can't be a methene. A methene has only 1 carbon. So that's why it can't work that way. Okay, so for instance, an ethene which has 2 atoms, this is a structural formula. The number of atoms follows a series: 2, 3, 4, 5, 6, and so on. And as the number of atoms increases, so is the boiling point increasing. So does the boiling point increase. With more number of atoms, you have longer chains. So it is more difficult to break those chains. It's a higher force of attraction. And so you require a higher energy. And that's why the boiling point and the melting point increases. So the boiling point of propene is higher than the boiling point of ethene, even though all of them are gases at room temperature. They are below 0 degrees Celsius. But the boiling point of propene is higher than the boiling point of ethene. With longer chains, it's more difficult to break the bond, so you supply more heat. So higher boiling point, higher melting point. Now we can form the structural formula of one alkene like hexene. Let's form hexene, for instance. Hex is 6, so it has 6 carbons. So let's write out the carbon atoms as C, 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 C. 1, 2, 3, 4, 5, 6. We have it. The first two will form a double bond, as I already told you. The rest are single bonds, single bond, single bond, single bond. And then you begin to represent the hydrogen, the hydrogen, the hydrogen. If you notice, the second carbon atom will not have any hydrogen on the upper part of it for propene, butene, and so on. But the rest we have it. So you have hydrogen here, hydrogen here, hydrogen, 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 and then the final one, hydrogen here. So if you check, we have 6 atoms of carbon. 1, 2, 3, 4, 5, 6. But how many atoms of hydrogen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which corresponds with the proper formula of hexene. Remember, the general formula is C2 Cn H2n. So since there are 6 carbons, it will be C6H12, and that supports our illustration. All right, we need to understand some of the reactions that alkenes can undergo. One of the reaction is the formation of alkenes from alkanes. Good. Okay, look at this. This is an alkene with a double hydrogen carbon-carbon double bond. So an ethane, for instance, when subjected to a high temperature of about 800 degrees Celsius, provided with a steam, a very hot steam, can form an ethene, and then also hydrogen is released. Remember, ethane is saturated. It's a saturated hydrocarbon. But the ethene it forms is unsaturated plus hydrogen. So hydrogen is produced. In fact, this process is what we call cracking. When we get to petroleum products or crude oil, refining and cracking of petroleum products, we'll talk more about that. The essence of cracking is usually to break down large molecules to smaller molecules. The large molecules will be broken down by a process we call thermal decomposition using heat, and mostly with the presence of a catalyst. One of the examples of a catalyst that can be used, especially in the laboratory, is aluminum oxide. So when an ethane, for instance, which is an alkane, is subjected to heat in the presence of a catalyst, the large molecule breaks down to a smaller molecule, and also hydrogen is released, and that is what we call cracking. We'll talk more about that when we get to petroleum products. But generally, cracking is done to produce smaller molecules from larger molecules. Those smaller molecules are usually, for instance, if you check, the reactant itself is an alkene. The reactant itself is what? It's an alkane, which is saturated. But the product is an alkene, which is unsaturated. So the alkene can be used to produce more substances like plastics, like paint, like shampoo and other products. So usually the product of when petroleum products are cracked, or when cracking is done to petroleum products, you produce substances that are more reactive. For instance, a saturated ethane having undergone cracking by heat and maybe with a catalyst, we produce an unsaturated ethene and hydrogen is released. Okay, that's one of the reactions with involving alkene. Another reaction is alkene itself can join with hydrogen to form alkanes. In fact, that's like the reverse of the first one. Cracking produces this. Cracking of ethane produces ethene plus hydrogen. Now, ethene plus hydrogen can produce ethane again. And that, of course, will require heat with pressure and the presence of a catalyst. Now, if you notice, the ethene itself is unsaturated. Now, when it combines with hydrogen, it forms ethane that is saturated. This combination reaction is what we call addition reaction. So an alkene can undergo an addition reaction. An example is ethene combining with hydrogen to form ethane. Usually when alkenes undergo addition reaction, they form saturated products. For instance, ethene, which is an unsaturated alkene, combining with hydrogen in the presence of heat, pressure, and a catalyst, will form ethane, which is saturated because it has a single carbon-carbon single bond. The reactant itself has a carbon-carbon double bond. You can also see another example when this same ethene with a carbon-carbon double bond combines with water to form ethanol. This ethanol itself is saturated because it has a carbon-carbon single bond. So an addition reaction turns unsaturated alkene into a saturated compound. Example, alkane or even alcohol. Alkane or alcohol. In fact, this is one of the ways we can produce alcohol. This reaction itself, this second reaction, is reacting ethene with water, an addition reaction, to form ethanol. Ethanol itself is saturated because it has a carbon single bond. But the reactant itself, which is ethene and water, ethene is unsaturated. In fact, ethanol is a good solvent. It can dissolve so many things, and it is also used as a disinfectant because it kills germs. It can be used as a hand sanitizer in hospitals or to disinfect floors and the hospital environment, or materials that are used for medical use. Okay, and we talk about also polymerization. Polymerization is what happens when monomers monomers, which are single units of organic molecules of organic substances. When monomers join together to form a long chain of a molecule. An example is an alkane molecule. In fact, we have 6 alkane molecules here. 1, 2, 3, 4, 5, 6. 6 different alkane molecules. Now, you know, 6 different alkene molecules. 6 different alkene molecules. 6 different alkene molecules. Each of them is a monomer. Each molecule is a monomer. Each molecule is a monomer. Now, a monomer, and you know, alkenes have a carbon-carbon double bond. Carbon-carbon double bond. Now, when these molecules, individual monomers, join together, they form a straight chain of long carbon-carbon single molecule, single bond. So, and that is what we call polymerization. So polymerization produces a long chain of molecules from several monomers. So when you have several monomers that join together to form a long chain of molecule, we call it polymerization. An example is this 18. This 18. When this 18, 6 molecules of 18 join together, they form a long chain of a long chain which we call poly-18. Now a poly-18 or polyethene, long chain. And the chain can be many thousands of carbon atoms. That's polymerization. Okay. Now, one of the ways we can test that a substance is saturated is unsaturated. One of the tests for unsaturated. In fact, a major test for unsaturation is a reaction with bromine water. Bromine water is when bromine is passed through water, a solution of bromine and water. And that the solution of bromine and water forms an orange solution. So a mixture of bromine and water forms an orange solution. So when alkenes, for instance, combine with bromine water, when you place alkenes inside bromine water, or when you add alkenes to bromine water, there will be a reaction, and the reaction will produce a color change. In fact, the orange color of the bromine water will disappear. It becomes colorless because it will now form a different substance, which is 1,2-dibromoethane, which is colorless. So if the orange color of the bromine water disappears, it means there was a reaction. And reaction can only occur if the hydrocarbon is unsaturated. An example is 18, which is an alkene. If this was an alkane, like 18, and you react it with bromine water, there will be no reaction. Or you want to react with the bromine water, there will be no reaction. So the color of the bromine water, orange color of the bromine water, will not disappear. And so when we have a positive test, when there's a reaction, the orange color of the bromine water will disappear. It becomes colorless. And so you can conclude that it is an unsaturated hydrocarbon, because the color disappears. It forms after the reaction, and it forms a substance, a new substance that is colorless. Now remember, alkene is unsaturated, so it can react with bromine water. Alkanes are saturated, they cannot react with bromine water. So with alkenes, there will be a reaction. The orange color of the bromine water will disappear. With alkanes, there will be no reaction. The orange color of the bromine water will not disappear. So that's a test for unsaturation. Just like alkanes, alkenes also have isomers. And remember, we define isomers as organic compounds with the same formula but different structure. Same formula but different structural formula. Okay, for instance, this butene or but1 in C4H8. C4H8 can have other arrangements with the same number of atoms of carbon. Like here, 4 atoms. We have 4 atoms of carbon. 1, 2, 3, 4. 8 atoms of hydrogen. 1, 2, 3, 4, 5, 6, 7, 8. All others have the same. If you check, 4 atoms of carbon. Also 8 atoms of hydrogen. The same thing for this one, 4 atoms of carbon. Also 8 atoms of hydrogen. Okay, so they have the same formula, but different structural formula, different structures. And so they are isomers. Isomers are organic compounds with the same chemical formula, with the same formula, but different structural formula, just like isotopes. Isotopes are atoms of the same element with the same proton number or atomic number, but different nuclear number or mass number because they have the different number of neutrons. Okay, because of the difference in the structure, they will have different properties. In fact, the ones with longer chains will have higher melting and boiling point because the longer chain means more attractive force between the carbon atoms. So you will require more energy to separate those atoms. And because you are going to require more energy, it means you will need to supply more heat. So it will have a higher boiling point than these branched out ones. This particular one is, if you notice, just like I explained when we're looking at isomers of alkane. When we're looking at isomers of alkane, I explained that initially what we had here. Okay, sorry. Let me clean this a bit. Initially, what we had here was a hydrogen atom. We had a hydrogen atom. And if it was in this state, it's basically a propene with 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6 hydrogen. So this was originally a propene. So I can even clean this to show you that this was originally a propene. This was originally a propene. This was originally a propene. Propene, which is an alkene, 3 carbon atoms and 6 hydrogen atoms. So it's a propene. Now, if one of these hydrogen atoms, this particular one, is replaced with a methyl, so it's been replaced. This whole thing that has replaced it is a methyl. This part. Okay, let me zoom in properly so that we see it better. This whole place that has taken the place of the initial hydrogen atom is a methyl because it has 1 carbon atom. If it had up to 4 hydrogen atoms, would have called it methane, but it's a methyl, and it is attached to the second carbon in the original chain, straight chain, And so this is the way we name this. Because it is attached to the second carbon, you say 2-methyl propene. And so that's why the name is like this. So I reveal it. 2-methyl propene. 2-methyl propene is attached on the second carbon double bond, and it is a methyl that is attached to it. So it is a 2-methyl propene. It's an isomer of but1-ene or even but2-ene. You know. Now, why is this one called but1-ene and this one is called but2-ene? If you notice, the double bond is on the first one, but1-ene. This one, the double bond is on the second one, but2-ene. So the double bond, where the position of the double bond determines the name. You know, when I was explaining to you how we got hexene, this hexene, the double bond is on the first one, so this is actually hex1-ene. That's the proper name I would have called it, hex1-ene. If the double bond was on the second carbon-carbon atom, would have called it hex2-ene. And that would be another isomer of hexene. In fact, some hydrocarbons or organic compounds can have several isomers. You know, so these are the isomers of C4H10. Let me clean it up. C4H8, sorry. They have the same formula, but different structure or structural formula. So the name, in other words, but1-ene, but2-ene, 2-methylpropene are all isomers of C4H8. They will have different properties, as I've already explained, using alkenes. Okay, so that's about alkenes. We look at other families of organic compounds like ethanol, alkanols and carboxylic acid. That will be what we'll look at. Alcohols and carboxylic acids. So we'll look at that subsequently. So some of the questions you may get are like, name the two simplest alkenes. Now draw their structural formula. What makes alkenes react so differently from alkanes? 18 can polymerize. What does this mean? What does it mean for 18 to polymerize? By the way, can alkanes polymerize? The answer will be no, because it's saturated, so it can't split to form longer chains, to add up to longer chains. Now it says propene is unsaturated. What does it mean? Now write an equation for its reaction with bromine. How would you turn propene into propane or propanol? All of these we have answered in the discussion. If you check the discussion, you will notice that all of these have been answered one way or the other. So this is a beautiful way of looking at alkenes. Polythene is, for instance, what we call polythene bags, nylon bags, which we use in plastic bottles, are polymers from several monomers of 18. When you have several long chains of those monomers, you have the polymers. So polythene is basically polyethylene. All right.